Good morning to you. Welcome to this lesson. Allow me to take you through some solution to problems concerning heat transfer by conduction. Last time I began by doing for you some examples here, but I did not go so much far. Allow me to go ahead and look at another example. For this case, we're talking about this question. So the question is two brick walls, each of thickness 10 millimeters, are separated by air gap of thickness 10 centimeters. The outer faces of the brick walls are maintained at 20 degrees Celsius. And at the same time, 5 degrees Celsius respectively. Calculate the temperature of the inner surface of the walls and compare the rate of heat loss through the layer of air with heat through the single brick wall. Allow me to first sketch out this diagram. Here we are having a brick wall. So if the wall is having two bricks, the inner surface and then the outer surface, but within this brick wall, there is another layer that I talk about. There's a layer which is separating the two bricks. So it therefore forms three layers. This is the first brick, called brick A. Okay, let me call it brick. This is, okay, this part we're going to have a bit of brick, the first brick. And then even here we shall have the conductivity of another brick. Then here we shall have the conductivity of air. So this is air, this is brick. And then this also what? It's also brick. So we're saying that heat transfer moves from region of higher temperature to region of lower temperatures. So as heat is traveling from this end to this end, the temperature shall keep on decreasing until it goes to 5 degrees Celsius from 20 that was given. So at the steady rate of heat flow, we shall have the rate of heat flow, the QDT, is equal to, is going to be the same rate that will be flowing out here. The QDT at this point they will be the same. So therefore, if you look at the thickness of this brick here, this is the length of the brick, I'm going to be A. And if the brick is 1, then even here is going to be also L what? We're going to be L of the brick, length of the brick. It is the same way for this brick here because of the same material of the bricks. So here then we have length of the air what? The air gap, like that. So that's what we have in this case. Very important for you to sketch what you're going to work out. If you don't sketch, then you're planning to fill out things. Okay. So that is it, what I have sketched now. Now I'm going to write down my equation relating heat flow and then the conductivity. We know that the Q, the T, rate of heat flow, is the same thing as the conductivity K. Now I'm getting from this point here. I'm going to from K, but this one is from the brick, times the temperature gradient. Here the temperature is moving from 20, it's decreasing from 20 to theta 1. Then divide by the length to make it temperature gradient times the cross-sectional area of that surface there. Now, if you look at the cross-sectional area, is that surface where heat is going to be flowing, like when it's going to be passing. If you look at now the surface here, the whole of the surface here is going to be the same up to this side. So you can just maintain that as A. So this will be equal to the rate of heat flow when comes to this point here through the air gap, which is a conductivity of air some quantity of air, times the area, cross-sectional area, times θ1 minus θ2 divided by the length across there. So this will still be equal to, hope you can see well, this will be equal to, still this will be equal to the heat flow here, which is also K B times A times temperature gradient, which is θ2 minus 5 degrees Celsius, minus 5, then divide by the length LB of that conductor, like that. So when we have those equations, we can treat any pair of the equation to give us what we want. So here the question asking us to calculate the rate of fluid flow, the rate at which it is, calculate the temperature of the inner wall of the bricks, temperature of the inner wall of the bricks. So they want you to calculate the temperature here, the inner walls. This one is here. This is the inner wall of this bricks, inner wall of this brick. I want us to find θ1 and θ2. So you're going to treat any two equations. You're going to treat two equations at the same one at the same time. So I can begin by writing up this equation here. Hope you can see this is 5. That is 5. So I'm going to have here, therefore, let me equate this one and this one here. I'll have KB times A into 20 minus θ1 divided by LB must be equal to, let me take it with this one here, must be equal to KA. KA then A into θ1 minus θ2 divided by L what? LA. That will give us the first equation. That will give us the first equation. So when we equate the two equations now, we can see that A shall go away in this equation here. Its cosine will go away to the equation. So that now we remain with, we're going to remain with, if I cross multiply, I'm going to have 20 minus θ1, everything times LA, which is equal to θ1 minus θ2, here time here KB, and then here time is also K what? Here KA, then times L what? LB. Call that to be equation 1. Call that to be equation 1. So after that, also treat this equation, the first and the last. After treating the first and second, treat the first and the last equation. This will be equal to, if I treat the first and the last, I'm going to have K BA times temperature gradient 20 over 20 divided by what? LB, which is equal to the last equation, which is KB A into θ2 minus 5 divided by again L what? LB. So now I can see that LB is here, LB is here, so that LB will go from the equation, and even KB will also go from the equation, A will go from the equation, and that should remain with the 20 minus θ1 is equal to θ2 minus what? Minus 5. So that I can make one of them subject. I can say that θ1 or θ2 is equal to, bring from this side, θ2 is equal to 25 minus θ what? θ1. This is equation 2. That was equation 1. Are we together? Now I have treated the first equation and the last. Okay. Now go back with this. You can also treat go back. I mean, get this equation here. Get this equation here. We can decide to divide the two equations. If we put this equation and this one here, let's put the value of K1, we have it. Let's do did they give us anything here? Let's check. We have the conductivity of air, and then the one on the base we have. The only thing we don't know is the length. We also have the thickness of the brick. We can put it there. So I can now therefore say that. Now, for that equation, I'm looking for this. I'm going to substitute for theta 2 and substitute all these values here. Now, KB is equal to, let me put it, and then you can see. Thermoconductivity of air is given there. Then for the brick, 0.6. So 0.6 into bracket 20 minus theta 1 times thickness of air. The thickness of air there is, the air gap is 10 centimeters. So you divide by 100, that is 0.1. Must be equal to Ka, conductivity of air is 0.02. So this is 0.02 times temperature gradient here, which is theta 1, minus, put the value of theta 2 here, which is minus 25 minus theta 1. 25 minus theta 1. Then after that, you multiply it by thickness of the brick thickness, which is 10 centimeters, which is 0.1. Now, open the brackets. We're going to have 0.06 into 20 minus theta 1 being equal to, so also 0.002 into theta 1. So this theta 1 will add up here. Go to theta 1 plus this one, so it's going to be 2 theta 1 minus 25. Shall have now that. So I'm going to move this, but hope we can remember our equations. Yes, count them. I can go ahead and say that 20 times this, 20 times that. You can multiply from that and we give you the answer. We have 20 times 0.06. 0.06, that is 1.2. We're going to have now 1.2 minus 0.06. Theta 1 is equal to, here is 2 times this is going to be 0.004 theta 1 minus, if you multiply 25 times 0.002, you come up with 0.05. We can also solve that. Let's bring all the theta this side, then on the other side. We're going to have 1.25 being equal to, bring it on this side. If you have 0.004 plus 0.06, it's going to be 0.064 theta 1. So divide both sides by 0.064. Both sides by 0.064. The answer we're going to get there, we can write it 1.25 divided by 0.064. So if we check, I get 19. So my theta is equal to theta 1 is equal to 19.5 degrees Celsius. If you check with our answer, which is here, you can see it. Theta 1, 19 point, this one, Celsius, degrees Celsius. Now, after getting that value of theta 1, you can now get theta 2. So theta 2, you're just going to substitute theta 1 here. So you're going to now say that theta 2 is going to be, we're going to have theta 2 here. This is the value of theta 1. We can now go back and then we substitute here to give the value of theta 2. Therefore means that the 2, so from here I'm having theta 2, which is equal to 25. Then my theta 1, which should go there is 19.1 5. To do that simple mathematics, I'm going to get 25 minus 19.5. That is 5.5 degrees, 5 degrees Celsius. If you compare with the ones that we have there, it is the same with that. So what is it? The second part of this problem was, you can pause the video and make your notes, because I cannot wait you to do that. Now we're going to, the asking us that calculate the temperature of the inner wall, of the inner surface of the wall, and compare the rate of heat loss through the layer of air with that of the single brick. So now we want to compare it now. Okay, we're going to get the ratios. We have now to get, remember that the heat rate here must be the same at steady state. So that means the values must be almost the same. We're going to get the heat loss at this, the rate of heat flow at this point, and also the rate of heat flow at what? At this point here. Okay? All right. So let's get off. Okay, so we're going to have and what by what is here? Theta 1 is equal to 19.5 degrees Celsius, and theta 2 is equal to 5.5 degrees Celsius. Having this value added and erase everything here. Okay. Here. So that's what I have. Now I can therefore try to compare. You know that now I'm saying that the dt is equal to k. This is not so clear. I can throw it. It's equal to k. Then actually this is k of the brick, and the brick times the area. Then bracket theta, we need to know it's 20. 25 minus theta 1, which is 19.5. Is it? We'll be sure about that. Here is 20 to 25, here is 20. And then here is 20, here is 19.5. Okay. So this is 20. Divided by the length of L1 brick. So come on, substitute. I'm going to put the brick. If you remember it, there. We're going to put the brick is equal to 0. So you have 0.6 times the cross-sectional area. So here we can leave it there. Then minus 0.05. Then the length of the brick, the brick thickness, which is 10 millimeters. This is 0.1. So we can therefore now say this. We can say this is going to be equal to. It's going to be equal to 0.6 times 0.5, then divided by 0.1. So this is 3a. This is the Q, the T. Through the brick, through a single brick. Yeah. Then you go to the next one also through the what? Through the air gap. Through the air gap, through the air gap, we shall now have the QDT being equal to K of A times the area. Then here now that's one began from 19.5 and then it went to 5.1. Then by then you see the same as 0.1. This is going to be equal to 0.02 times A into bracket. If subtract this is 0. This is 14 divided by 0.1. So our answer here is going to be equal to 2.8 A. After getting this answer, now we're going to the ratio. We want to just find the ratio of heat flow through air gap and also through what? Through the brick. So we're going to divide. We call this to be B, and then this is A. dq over T divided by dqa over dt. This is equal to 3 divided by 2.18. All of them have A, so this A will cancel. So this will now be equal to 3 over 2.5, which in ratio form divide it as 2 to what? To 8. When you find that, you find that the rate of flow through the two materials is almost the same. That's why we say the rate of heat flow is what? Is constant at steady state, but it's not the same throughout because there is heat loss to the surrounding. At a given point, they can ask you why the two values different. You tell them that it's because of the what? The heat loss to the surrounding. Are we together? Okay, so with that, you can write down that. Let's go to the next. A window of height 1 meter and width this contains double glazed unit of 2 single glass plates, each of thickness 4 millimeters, separated by air gap of this. Calculate the rate at which heat is conducted through the window if the temperature of the external surface of the glass at which equals Celsius and that respectively. They have also given us the conductivity. So what you do here is to draw. The first thing you have to do is to sketch the diagram you've been given. And you put everything that is there before you can continue. If you cannot do that, then don't waste your time doing the question. Because here is that interpretation has what? Has failed. Okay, so I'm going to draw this. Now, the first thing you have to know is how many surfaces are there. In most cases, there are 3. In most cases, there are 3. In a few cases, there are 2. But you have to be first of thinking, are they 3 there? The same that a window of height 1 meter width. The window of height 1 meter width. 1 meter height and then width 1.5. That means the area of this window here, A, is going to be equal to 1 times 1.5, which is equal to 1.5 meters squared. That is the area. Contain a double glazed unit of 2 single glass plates, each of thickness what? 2 millimeters. So now here we have a thickness of this is 2 millimeters here. This cross-sectional area, this area remains the same throughout the whole of this because it flows like this. I don't know if you can see me because of now put off there. I was saying that the cross-sectional area here, A, is the same for here, here, and here. Don't matter so much. After finding that one is the same. So the rate of heat flow here will also be the same even now. I think it comes out here, dq dt, like that. Are we together? Now, after if we have gotten that one like that, then we can now put the temperatures of every point. And I told us now you begin demarcating by looking at the highest temperature, look at the small one. So they say now that a window of height that contains double glazed unit of single glass plates, each of thickness, but separated by air gap 20 millimeters. Okay? So this window here is 4 millimeters long. This one is 4 millimeters long. The window is 4 millimeters long. And then the separation of the air gap is 2 millimeters. Even here 4 millimeters. This is the only thing that value that are different. Is that this length that the area here will be the same. So the temperature here, the highest this thing is at the surface of the window is at 30 degrees Celsius. Then here we do not know, and here we don't know. They will just tell us the temperature of the outside of the window. That's how you think about these questions here. But you have to be very keen on them because you can easily do what? Fail. Are we together? Now, after that, we know that the Q, let all it flow, the Q, all over the T is equal at this point. I'm going to call it to be the window, and this one is air. It's also window. So it's equal to the conductivity of the window, but here, the window they're using here is glass. So I'm just putting it G. The magnitude of glass times cross-sectional area, then multiplied by the temperature, which is 30 minus theta 1 divided by what? By 4 millimeters. So you convert it into meters. This is 4 times 10 power negative what? 3. All together. Now after that, the area, put the area here. Let's forget about it. Squared. After this is equal to also the rate of heat flow at that point, which is conductivity of air times the cross-sectional area times temperature theta 1 minus theta 1 2 divided by that this is the thickness is 2 times 10 power negative 3. This is equal to outside here, which is equal to kg A into theta 2 minus 20 divided by how many? By 4 times 10 power negative 3. So now we have 3. Simple like that. We can equate the first and the second one, then this after this one. It is okay. So I'm going to begin by equating the first and the last. I'm going to have therefore that kg. After they ask us exactly, they are asking us to calculate the rate at which heat is conducted through the window. Okay? Through the what? Through the window. That means that we need to look for this temperature here, theta 2. Yes, so you have to treat this equation that what? At once is so Ka into 30 minus theta 1 divided by 4 times 10 power negative 3 must be equal to this one here also, which is kGa into theta 2 minus 20 divided by 1 4 times 10 power negative 3. Now this one here will cancel with this one will cancel with this one will go with this. We're going to have 30 minus theta 1 which is equal to theta 2 minus 20. Are we together? To doing that like that, then you cannot make one of them subjective. How to make it a subject? So theta 2 will be equal to, take it, let's say 50 minus theta what? 1. I call that to be equation 1. Share. Okay. So after that, you can continue. You can continue. So to equate now this equal to the equation this one and this one, we shall have also kGa into 30 minus theta 1 divided by 4 times 10 power negative 3 being equal to Ka times A into theta 1 minus 1 theta 2 divided by 2 times 10 power negative 1 3. Forgetting now that you can see that this one will with this. Just bring the material of glass and the one of beer. The one of glass is 0.72. 0.72 into 30 minus theta 1 is equal to the one for glass 0.025 into theta 1 minus 1 for theta 2 is 50 minus what? Minus theta 1. And here we divide by 4 and we stand for negative 3 divided by 2 and stand for negative 3. I know this one goes here once, it goes here 2 times. You can simplify that by that. Moving this equation here, now we have, now I multiply this to this side, okay? That I have now 0.0 times 30. I can now get this answer. 0.72 times 30, which is 21.6 minus 0.72 theta 1 being equal to 0.025 theta 1. Now we can add theta 1 here. This one will be 2 of them. If you multiply 0.05 times 2, 0.05 times 2, then we're going to bring 0.05. So let's put it 0.05 theta 1. Okay, then minus 50 times what is there? 0.025. The times 50 minus 1.25. Okay, after that now I can take it on the side. So we have 22. Now we can add it. 22.85 being equal to 0.05 plus 0.072, which is 0.77 theta 1. If I divide that to 2.85 divided by 0.77, theta 1 will be equal to 29.27 degrees Celsius. I'm putting it to 180. That's theta 1. Find theta 1, I can put it here to find theta 2. So theta 2 is going to be equal to 50 minus that value there. Again, minus 50 is going to be around 20. What? 3 degrees Celsius. This is 7. 4 degrees Celsius. So I'll have that like that. I remove this and I take this value here. Now, I'm finding that we now have the two thetas, but we want rate of heat flow. The Q, the T is what we want in this case. So what we do, you go back and substitute the original equation, which is 0.72 times the area which already got was 1.5, and drop in bracket 30 minus 29.7 divided by this one times F103. We can now get that answer. So this will give us 0.72 times 1.5 times open bracket. Okay. When is that? Okay. This will give us the answer, which is what? Well, now the answer, which is 164.1 joules per second. 7 joules per second. So that is it. That will get for that. Calculating that. You can see this what we get from here. So we get from here. So here they got shape of this 2.4. It's some like what you can see here. Then due to rounding, so good one about it. Okay, the next number. Let's do number 4. Then I can just guide you on this. A wall 6 meters by 3 meters consists of 2 layers. So there are 2 layers here. A and B of the connectivity that is expected. The thickness of the layer is this one. The inner surface of the layer is at this temperature, while the outer is at this temperature. That way the temperature of the interface of A and B. This is too simple. There are only 2 faces. So you always note out the force, okay? Don't just mean that every time they're going to be 3. Sometimes they're all going to. Like for example, here, this wall is 6 by 3. This one you multiply 6 times, this will give you the what? The area. Okay? 6 times this will give you what? The area. Right. When you have the temperatures here, you have some activity, you can calculate the temperature, the interface, then you find the rate of heat what? To the wall. We have another question here, number 5. Let's do this number 5. Okay. Number 5. Example 5, you're saying that copper rod 2 meters long. You can deal with sketching this. 2 meters long. And diameter 3 centimeters. Diameter 3 centimeters. So copper is 3 meters long. Diameter 2 meters long. Diameter is 3 centimeters. So it is obtained at temperatures 'This temperature, it is at this point is at 300 degrees Celsius. Where we have it at this point is 40 degrees Celsius. This point is at 50 degrees. And the conductivity that are given here, one for copper, is 380. Kilo of copper is equal to 380. And then the one for further saying that. Let me first show you this question interpretation here on this case. Say copper rod 2 meters long and of diameter 3 centimeters is lugged. One end is maintained at 300 degrees Celsius, and the other end is placed against 3 centimeter thick cardboard disc of the diameter of the rod. The free end of the disc is maintained at 40. Calculate the steady temperature and this, okay? So the middle one here is the cardboard. This one is the same diameter And if theta 1 it is 0.2. Okay, of the cardboard, and we call it board. It's equal to 0.2. It's equal to 2 points for that. All right. Now we know that the rate of heat flow, Q over T is equal to, you can put the QDT, but put Q over T is the same. Oh, not with square. It's equal to K, C, times area. And temperature is 300 minus what? Theta divided by what? Length L. Total L of the copper is again equal to KB. Position L remains the same. Times theta minus 40 divided by what? Length of the what? Of the copper core. From here, all this is copper board from here. Copper board. This is copper. That's side. After that, now we know this length here. The length is something as thickness. So here we have, so this is going to be equal to 380. This just gives us the egg when you cancel. Into 300 minus theta divided by the thickness, which is 15 centimeters. So this is going to be 15 times 10.52. Change it to meters. This is 0.2 times A into theta minus 40 divided by what? 15 times 10.52. Thickness was the same. If you level it, cancel this one, cancel that. This one, with that. So remain with this will be equal to 380 into 300 minus theta equal to into A minus what? Minus 40. You can multiply this and see what it gives us. You have 380 times 300. No, I don't see it. I'm telling us it's 1,114 then 00 minus 380 theta is equal to 0.2A. 0.2 theta, not A. 0.2 theta minus, here is, multiply that, what your time is 0.2, it is 8. 8. Let the like terms bring the side, bring the side. Not been a 114008 will be equal to 308.2 theta. Then you divide them 114,008 divided by 78, 0.2. So theta is going to be at around 299.9 degrees Celsius. That's what the is going to be. Okay, I think it's not the same. There are some error here. Let's try to correct it. They're not the same length. Thickness of the copper 3 centimeters. This one is 2 centimeters. This one is 2. And the same for negative 2. This is 3 times the same for negative 2. This negative 2 can go with this one. Let it go to the main width. 380 times 300 minus 380 theta. And then divide by 2 because of 0.2 theta minus 8 divided by 1. 3. Then it was multiplied. When we get theta, the answer will be 291. 197 meters. That is what you're going to find. After find that temperature there, you go back and you substitute, and then you find Q over T. Put it in one of the equation, put it here. You know this, then you put it there, which is equal to Kc, then into 300 minus theta, divided by 2 times 10 power negative 2. Then after substituting, you're going to find this value in joules per second, which is 1.8, 1.183 joules per second. That is the steady state, that is the rate of heat flow. Then the quantity of heat flowing against the junction in 10 seconds. Just come and multiply that times 10. What's going to happen now? Q will be equal to that energy, which is 1.183 times the value of given here, which is 10 minutes. So you take it to seconds, 10 and 60. You're going to get the value there around 700, 9.8 watt joules. That will be the energy. Great. That's the energy you get. So we're going to come after that, we're going to come and try this question. Try one by one questions. Next, if you get a challenge, then you can ask me about it. So when we meet next time, I'm going to teach you about this surface series. That's what I will teach you about. Okay, that is it. Because we finish passing through here, we shall just come on. So for now, allow me to stop here and see you next time. Goodbye.